One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. Yeah. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I am, baby. I'm yours. Yes. You got my future in your hands, baby. I'm yours. I'm gonna be yours. And here I Like a fool, I waited way too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Then that time I waited, said goodbye. Yeah, baby, I won't back out, ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. I'm yours. You got my future in your hands, baby. I'm yours. I'm yours. And here I am, baby. I'm yours. You got my future in your hands, baby. I'm yours. And I'm gonna be yours. And here I am, baby. I'm yours. You got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited way too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Then that time I waited, said goodbye.
All right, let's get this show on the road. Hey everybody, how's it going? Ooh, my face is awfully big. Welcome. We are here on Friday, the 3rd of April. So doing all kinds of stuff today. So this is welcome. This is our first multivariable stream. We're going to be kind of trying to work this out over the next couple weeks, the next rest of the school year. Let's be honest. So I just want to preface by saying I can see what you're doing in chat. I can see all that. Just like I want to start off with a couple things. First of all, most notably, hey, how are you doing? I'm really interested, obviously, in what's going on in your lives and how you're doing. We're going to try to get some learning done over the next several weeks. But I just want to emphasize your health, your safety, your sanity comes first. I want to be as flexible as I can be with you while still getting some stuff done. But if you're in a tough situation, please talk to me. Please communicate with me. Oh, hey Daniel, you can hang around, whatever. I guess he gets notifications when I go live. All right, so we're gonna talk about today a little bit about what's going on with marking period 3, kind of what's graded, what isn't, what's happening. Talk about some of our goals for marking period 4, and then we're actually going to do, if you're up for it, a little review of 16.2 and 16.3. I know some of you have probably done readings on this and all kinds of things, but let's talk about it. So there's up on my MCPS. I just updated it today. There's kind of an updated tasks list and some updated buttons. So I'm calling this phase 1. Whereas physics is doing things week by week by week, we're doing things a little bit more informally. So this is kind of phase 1 of what we're doing, and it's going to run as this suggests from today up until the 17th. Why the 17th? Because the 17th is the new, as you probably are aware, the new end of marking period 3. Is the new end of marking period 3. There's a couple things I would like you to do over the next 2 weeks. First of all, there's a contact survey. It's very similar to the one on for physics. If you did that one, and if you haven't done that one, you should do them both. Just so that I can get an idea of like what's going on with you. Do you have a computer? You know, because I know for some of you, things are just fine. You're just bored. For some of you, you may be dealing with more stressful situations at home. You up to and including people being sick, or even just both your parents are trying to work from home and the computer is occupied all day and there's no chance for you to like tune into streams or whatever. So I want you to fill out the contact survey so I know what you need and how to work with you. There's some reading and stuff that I'd like you to do, 16.2 and 16.3. So these are on line integrals. 16.2 is kind of the basics of line integrals. We'll review that today. Okay, I misspelled integrals, so that's fine. 16.3 is the fundamental theorem of line integrals, which is pretty cool. Complete the 16.2 and 16.3 problem sets. So over the next 2 weeks, I would like you to turn those in. These will be the last new grades in marking period 3. We're really only supposed to give out like 2 new grades. So that's going to be the 2 new grades. We'll figure out how to quiz and how to assess on these things later. So these 2 will go on marking period 3. So I would like you to do them. There's 2 little links. You can turn in pictures. You can turn in, Google Doc, whatever you got. I have here a stack of exam corrections from, some from physics and some from multi. I have here a stack of exam corrections that I need to go ahead and put in. If you haven't done your exam corrections yet, do your best. Obviously, for some of you, I have CGA's exam right here. For some of you, if I haven't given your exam back yet, it's going to be hard for you to do corrections. So we can work with that. I can send you pictures or whatever of it. But if you can turn in your exam corrections, just email those to me so I don't miss them. I don't want to have a turn-in link if not everybody is turning them in. Most of you have done them by paper. There's a little survey where we can request problem set questions to go over next week on our stream. And then tune into our live stream. We're going to try at least to do Fridays at this time from 12:45 to 1:30. Why from 12:45 to 1:30? Well, this is a very rough and scrubbed version. This is kind of an internal teacher document. So of the rough schedule that they want us to do most weeks. Now, there are some exceptions to this, like the upcoming spring break, where over Easter and various holidays, they don't want us giving you things to do for work. But the basic idea is that on Mondays, we're going to be releasing new content. So Monday to Tuesday is where I'll be putting new things on my MCPS for you to check out. And then the idea is that there are these blocks that we're trying to do. So if you have an English class, they're supposed to meet like every other day at similar times. Now, this doesn't always mean streaming or Zoom calls or whatever. This can also mean just office hours. The teacher promises to be available during these times. I just want to note, we're going to try to stick to this, sort of. We're being flexible. And the reason we're being flexible here is I am also working from home with 2 kids and a wife who's working 40 hours a week. And so, for instance, Wednesdays are not necessarily a good time for me to stream from 12:45 to 1:30 if somebody else is on a call. So, we're going to try to do our best to announce everything on my MCPS and over Remind. If you ever have any questions, let me know. If you miss a stream, it's not the worst thing in the world. They'll always be posted on YouTube. But just communicate with me. Check my MCPS for the next 2 weeks or so as this is all shaking out into some kind of permanent structure. We're going to have to play it a little bit by ear. James, can you turn those problem sets in? Yes. Anything from marking period 3 that you have not yet turned in, please send me an email. What if you need to retake quizzes? And the answer to that is, I don't know. I'll work it out. I'll figure out something if you need to retake a quiz. I can send you the file. You can send it back to me. I don't know. This is a smaller class. We can do things a little bit more informally. But if you have questions like that, please pop them in the chat so that I can write them down, because I need to have a list for myself of questions that I need to answer. So I will, let's see. So things to do. So yeah, James, or anybody who has past problem sets, just email them to me, so that so past problem sets, quiz retakes, because some people will need quiz retakes. Great. So we're going to try to stick to the schedule. Obviously, if we run a little bit over and you need to bail, we'll be looking at that. Okay. So we're going to try to do this and then hopefully be ready for the aerospace, or not the aerospace, the physics stream soon. All right. So with that in mind, our goals for marking period 4, I'd like to be able to finish Unit 3 and give some kind of take-home exam. So, I'd give you like a whole week and a set of problems, and you'd submit your solutions to those, and I'd make I would make them so that I'm fine with you collaborating on them. I'm not going to prevent you from collaborating, whatever. Like, you probably need to talk to other human beings who are not your parent or your pets right now, and so Nick, this will be up later. So if you need to bail, that's just fine. And we'll get as far through Unit 4 as we can. Again, there's no official word. I would be shocked if we went back to school. I think we're going to be doing this through the end of the school year, which is sad. I'll miss you all, and we might not have a graduation. But if it helps any, R Part 7. I thought about that. I just don't know how many people have access to R at home. There was actually a really mean little meme that I was thinking of sharing with you. Let me see if I can find it real quick. It's worth it. Hold on. That I was thinking of sending out on April Fool's Day. And then I decided that it was really mean. Which was, pretending to be a screenshot from a governor's conference. Breaking news, Maryland students to repeat current grade. I thought of sharing that with you all, and then decided that was really mean. Is 16.1 also due? Yeah, that's yes, 16. Actually, I think if you check, on the thing, I'm not actually sure I assigned you. Did I assign you questions for 16.1? If there's questions assigned for 16.1, then we should do them. There are 16.1 questions assigned. Good question, Bruni. Yes, 16.1 will also be due, because we assigned that before we left. So I'll put up a link for that. We got the next 2 weeks to do it. It's okay. It's okay. Sorry, James. Another one. It's really just like looking at pictures of vector fields. So, free Minecraft accounts. Yeah. Well, we'll figure it out. It's going to be a 1,000-person Zoom call for graduation. It'll be great. Okay. Well, let's talk a little bit through. Keep the questions coming. Let's talk a little bit through line integrals and see if we can't fill out the next half an hour and do some things. So we started talking about these just before we left, but obviously didn't make a ton of progress. So what the heck is a line integral anyway? You may have done readings, you may have watched some of these videos. What a line integral is just like other integrals. It's a summation of a function over a bunch of small steps, right? We used to have the idea of like, some function, and here it was, and we would kind of cut it up into these little sections dx and integrate it that way. With the height of the function being f of x. Or we, with double integrals, we'd tile our area with all of these little dx, dy little tiles. Well, here what we're doing is we're still cutting up a function into tiny little bits and summing it over little steps. But now our steps, instead of being these nice little straight little linear pieces here, what we're doing is we're stepping along sections of a space curve. We're taking tiny little steps ds, whereas you might remember ds being like a little unit of arc length. We're taking tiny little steps along along some curve. And you can kind of imagine it looking an awful lot like a space curve, an awful lot like an integral from good old BC calculus, where you've got the height of some function. You're integrating some function, f of x or whatever, although I guess in this case it would be, f of x, y. You're integrating some function over this little path, and so you're kind of taking the height times ds, height times ds, height times ds, and you're kind of finding sort of the area of this weird little ribbon that meanders through a function. So the way we actually evaluate these, well, one of the kinds, and I'll talk about that in a second. The way we evaluate these, the line integral of some scalar function f, and again, it's important to note that this is a scalar function, f, is given this way. It's the integral of f ds. And we happen to remember what ds is if all the way back from unit 1, right? If I've got some space curve r of t, ds is just the magnitude of r prime dt. So when we actually evaluate these integrals, what we do is we put everything into parameter space, and then this ds becomes this little thing to tell us, well, how big a step am I taking, right? Because what we're doing really here is we're saying, I need to know how big this step is as I'm integrating over t from whatever, like, t initial to t final that I have, whatever my first t to my last t is. I need to know how big are these steps in actual xy space. So this is kind of my velocity, if you like. So we end up with these integrals of f times the square root of dx dt squared plus dy dt squared, or if you like, just the magnitude of r prime dt. I said there's two kinds of line integrals, and there are. The kind we're doing here are what are called scalar line integrals, where you're taking the integral of some scalar function over a curve. In a moment, we'll see the other kind, which are vector line integrals. And frankly, we'll be doing more vector than we do scalar. All right, so how do we evaluate these? First, we have to parameterize our curve in terms of t, or some other parameter. Then we substitute everything so that we're doing our integral dt. And then we get to integrate. So let's take a little example of this. And we did this one in class, but that was a long time ago. So let's try it again. So we're evaluating this function, 2 plus x squared y. So the function we're integrating is 2 plus x squared y. So you could imagine coming to different points on this curve and that function having different values at different places, right? But we want to integrate it over this curve. Well, it is a unit circle. And so I could guess maybe that a good parameterization of this would be like x equals cosine t, y equals sine t, and you'd be right. For t from 0 to just pi, because we're only doing the top half of the circle. In which case, when I take my integral, I'm going to be taking my integral from 0 to pi. My function becomes 2 plus, well, x squared y now becomes cosine squared t sine t. And I have to do this little square root here. The square root, though, is going to be, well, let's see, dx dt will just be, dx dt will just be negative sine t. Dy dt will just be cosine t. So I'm going to get, when I square these, sine squared plus cosine squared, or in this case, that's going to conveniently just be 1. So I end up with this integral 2 plus cosine squared t times sine t. This one turns out to be pretty easy. If I pull out the 2 part, I can do just 2, I can kind of separate it out. So I get this integral plus this integral sine t dt. I'm pretty sure this part is going to end up being 0, but let's just check. Do a little u sub here. Cosine t du is negative sine t dt. So I end up with an integral here of, I guess minus technically, u squared du from 1 to negative 1, or I guess actually, it's backwards, which is fine. This happens a lot. We did this in class. So here I'm just going to get 2 pi. From this one, I'm going to get 1/3 u cubed from -1 to 1. And so I get 2/3. Okay, no, I don't get 0 from that. I just get 2 pi plus 2/3, which is what we got in class. So I just kind of do my integral here. And then once, really, this, again, as we so often talk about, what's the real multi-part of it? This is the real multi-part of it. The rest of this is just like BC business. All right. There's plenty of examples of that and plenty of videos, so I don't want to overload you with too many more examples. If you have questions on the problem set, ones you can't solve, ask about them, and we'll go over them next week. If our curve is only piecewise defined, if our curve has breaks and jumps in it, well, then we do multiple integrals along the way. We just break it into C1 plus C2 plus C3. We do an integral for each little bit. All right. That's scalar line integrals. And scalar line integrals always have this awkward square rooty thing in here. Let's talk about vector line integrals, because these are what we're mostly going to do. So for a vector line integral, what we're doing is we're adding up the contribution of some vector field along a path, which is to say, I want to traverse some path, and all along the way, I want to say, like, what's the contribution of my vector field? And the classic example of this in physics is work. That imagine that I'm traveling along some path. I've got like a bead on a wire, and at every point, that bead is feeling different forces that are in different directions. Well, if I wanted to find the total work done by this force along the bead, it's not just enough for me to add up the force, because you might remember from physics that the force and the displacement have to be in the same direction. So if I want them to be in the same direction, I end up actually finding that what I need to do is take a little dot product. I need to add up only the parallel component of my vector field. So I'm kind of looking for how much is my vector field in line with my path. If I have a path that goes like this and a vector field that's very in line with it, here's my vector field, I'll get a very big line integral. If my vector field is opposed to my path, I'll get a very negative line integral. And if my vector field happens to be perpendicular to my path everywhere, well, how much of my vector field is in the direction of my path? A big fat 0. So what we're doing here, was there a place to turn in 16.1? Yeah, I'll put up a link for 16.1. I'll put up a link for 16.1 also, because I don't think anybody gave that to me. Yeah. So what the line integral is really trying to tell us here is how much of my vector field is going with the flow of my path. Well, it turns out that I want to take a dot product here. And I actually already have a great little vector to dictate what direction I'm moving. And that vector is a vector you might remember. It's t hat. It's our good old unit tangent vector, which you might remember as being r prime. If I know the path, it's r prime divided by the magnitude of r prime. So we turned it into a little unit tangent vector. And so what we find is that the line integral for a vector field looks kind of like it does for a scalar. It's still a ds integral, but instead of just some function, I'm now doing f dot t ds. Now, this does work in general. It is a thing that you can calculate, but you might recall way back from Unit 1 that calculating the unit tangent vector actually kind of sucked sometimes. It wasn't really that easy. So the question is, can we do better? Can we find a more useful equation? And the answer is yes. So this depends on us taking a moment to remember that if we kind of write our curve as r of t, right? Then again, what is our unit tangent vector? It's r prime over the magnitude of r prime. So what we can do is we can now rewrite our integral, f dot t. So here's our f. Again, we're putting things in terms of our parameter. Here's f, our vector field. dotted with our unit tangent vector. And then this is still ds. We still have the magnitude of r prime here. So what we find actually strangely is that in these vector integrals, hey look, I've got an over the magnitude of r prime and a magnitude of r prime. So what happens is that in vector integrals, we still have that ds. We still have that weird little square rooty thing here. This is, that square root of, dx dt squared plus whatever. But we also end up dividing by it when we have the t hat. So for vector line integrals, we don't need the ds, and we actually end up with this really nice form, which is just f dot r prime. So we just take the integral of f dot r prime dt, and that's actually a lot easier to integrate. I'm sorry, James. That will drive you even more insane. Yes. I don't know that. Yeah. Well, I don't want to say things. Yeah. In any case. All right. And sometimes you see this as f dot dr and occurs in other areas of physics. So if you actually look in your AP Physics thing, you'll find that work is defined not as force times distance, but as the integral of f dot dr, the line integral of f dot dr, because it's really a line integral. Yeah, Kevin, I'm gonna moderate that comment. This is a school stream. All right, cool. All right, so we're still going to do these, and practically speaking, we're going to still use this method f dot r prime. But the method is still very similar for any line integral. You parameterize everything, you figure out what you're integrating, and then you do it. All right, so let's give this a shot. So what we're doing is we've got this vector field that we're moving through, x squared I minus xyj. And we'll sketch that out in a second and exactly what that looks like. Ooh, that's a pretty axis. And what we're doing is we're traversing a path that goes along this quarter circle. So here's our path along the quarter unit circle, beautifully drawn. So let's try this. And it's cosine t sine t. So let's find our things. So first of all, what does our vector field f actually look like here? Rather than being x squared I minus xyj, I want to say, well, what is x, right? Where am I when I'm on this path? And the answer is x is always given by cosine t. So I can rewrite this as cosine squared t I hat minus cosine t sine t j hat. What is my r prime here? What is the kind of the velocity vector here? Well, that's going to be negative sine t I hat plus cosine t j hat. So when I set up my integral, I'm taking the integral, again, everything's in t from 0 to pi over 2, of the dot product of f and r prime. So when I take the dot product, I'm going to pair up these two. So I'll end up with come on. You can do it. You can do it. It just seems to... The dot product here of, so I'll get cosine squared, cosine squared t sine t, or I guess a negative cosine squared t sine t. And then I'm going to match these two up, and I get, hey, look, another negative cosine squared t sine t. So my final integral is just 0 to pi over 2 of negative 2 cosine squared t sine t dt. We can use the same u substitution we had before, which was cosine t du is negative sine t dt. So I end up here with an integral. Okay, when I plug in 0, I get from 1 to 0. So that's kind of backwards. Of just 2u squared du. So I end up with, what's that going to be? Just negative 2/3, I guess, if I work that out. negative 2/3. Now, it's kind of interesting that I get a negative value. That tells me that my vector field here is mostly directed against my path. That is, I'm mostly fighting against my vector field going along this path. Let's actually take a look at what that field looks like. Let's see if I can grab that for you. Vector field grapher. See if I can find a better vector field grapher. X squared I minus xyj. And again, I kind of only want to go like so this is from 0 to 2 and 0 to 2. You can't see it yet because I haven't brought it in. So this is what our vector field looks like. This is what our vector field looks like. And what's our path here, right? What's our path is our path kind of takes us up this way against the vector field. So you can kind of see we're opposing the vector field most of the time. And that's why we get a negative value. We have to do work against it, kind of. All right. There's actually one last way to write these, which is sometimes it's easier to think of our vector field as being written as like pi plus qj. Now here you could add for the 3 dimensions plus rk, although for our part we're usually just sticking to p and q. So what we find when we do this is we can kind of write it, we do this dot product, we can kind of write it as 3 different integrals, p dx plus q dy plus r dz, where what do we mean by dx? We kind of mean exactly what we think, which is just going to be like x prime dt. And so often writing it this way, p dx plus q dy is a little bit easier. And so I want to just show you what that means to write it like that. So we're going to do the same integral again. We should get the same answer. But let's remind ourselves that on this path, x is cosine t. So what is dx here? Well, it's going to be, negative sine t dt. Y is sine t. dy is cosine t dt. And then for our function, it's just important to note that p is whatever is the I hat component, and q here is negative xy. So when we set up our integral, right, what's p dx? Well, it's still just going to be, well, cosine squared is x squared times, negative sine t. So this is our p dx plus cosine t sine t. Here's q, and then our dy is here. All right, so that's a quick recap of 16.2, and obviously there's more problem set questions. I expect line integrals. This is probably the last topic that I would have chosen this year to do remotely. So we're just going to bear with it. We're going to do our best. I expect to have lots of problem set questions next week when we do our stream, so definitely ask them for that. I just want to give a quick preview of 16.3. And 16.3, the motivation of 16.3 goes a little bit like this. The motivation of 16.3 is, let's say that I've got this vector field, right? X squared I minus yj. And let's say, furthermore, that what I'm trying to do is I'm trying to take the line integral of that between 2 points, between 0, 0 and 1, 1. And I've got 2 different paths here that I could take. I could take y equals x squared, or I could take y equals x cubed, which is just a little flatter. Where it comes up. And the question is, what am I going to get from the 2 different ones? Well, I could do a line integral this way, right? I could choose, x equals t. Here I'm going to parameterize it. Y equals t squared. So in this case, dx is going to be just dt. dy would be 2t dt. And what we get is when I set up my integral from 0 to 1, I get, let's see, x squared, or I guess t squared for the first term, minus t squared times 2t. So this is me, again, this is x squared dt minus y, times 2t dt. So I end up with this kind of integral, which looks like t squared minus 2t cubed. When I take the integral, I end up with, let's see, what's that, 1/3 minus 2/4 minus 1/2, or like negative 1/6, I guess, assuming I did that correctly. 1/3 minus 1/2, yeah, 1/6. And I know I'm doing this super fast. If I do it this way, this is a totally different path, so we should expect a totally different answer. This would just be a warm-up that I would give you in class. T cubed, dx equals dt still. Dy is going to be, now what, 3t squared dt. So I now take my integral from 0 to 1. Let's see, I get x squared, so I still get t squared, minus, let's see, y gives me t cubed times 3t squared dt, or I guess what's this? This is t squared minus 3t to the 5th. So a totally different integral, which gets me, let's see, again, 1/3 minus 3 over, 3 over 6. Oh, well, that's going to be negative 1/6. So I have two different integrals, two different paths for the same function, and I get the same answer, which is weird. And this is a wonderful thing that we are going to talk about called independence of path. It turns out there's a lot of line integrals that are independent of path, which is to say the only thing that matters is where you start and where you end. The only thing that matters is where you start and where you end. And that because our two functions start and end at the same point, no matter what path we take to get there, we'll get the same answer. So let's talk a little bit about independence of path. And we're going to start by reminding ourselves of what a conservative function is, right? A conservative function is some vector field f that is the gradient of a scalar function. So its I hat component is the x derivative, its j hat component is the y derivative. If it's a 3D function, it'll be plus the z of this. That there's some original scalar potential function that exists. What we find, and one of the challenges that we had was how to go back, right? So if we think about this, this is the function from the warm-up, right? If our vector field looks like x squared I minus yj, what could our original function look like? Well, it could look something like 1/3 x cubed minus 1/2 y squared. 1/3 x cubed minus 1/2 y squared. That'll work out just fine. So this one was conservative. This one from our warm-up was conservative. And so this is really important. Conservative functions are going to be your best friend. And this is the fundamental theorem for line integrals, or how I learned to stop worrying and love independence of path. So what is the fundamental theorem of calculus? Remember that thing you learned way back when, that the integral of the derivative was just the thing itself. And this is, you've been doing this all for a long time. You might have forgotten that this is what you're doing, right? But if you take the integral from a to b of, let's say, 2x dx, you know that what you're evaluating is going to be x squared, right? You're going to be evaluating x squared. So you'll end up with b squared minus a squared. So what you used to do is you took the integral and then you just evaluated it at its two endpoints, right? And that's the important thing, is that you found the antiderivative and used two endpoints. Well, the fundamental theorem for line integrals is very, very, very similar. What we do is we say, if we are taking the line integral of a conservative vector field, that is, if we are taking the line integral of some vector field f dot dr, such that f is actually the gradient of some scalar function, then we don't actually even have to do the integral. If we can find the potential function, then what it is we just take the potential function at the endpoint, at the two endpoints, and subtract them. I just want to note, big F here is a vector field. Little f here is your scalar potential. Little f here is your scalar potential. And I just want to clarify, like, why is that? Why is that? Let's imagine for a second, and this is kind of a little freehand drawing that I'm going to make. Let's imagine for a second that we have some function, and here are a bunch of its level. Here are some of its level curves, right? So all right, so here it's level curves. And let's imagine that, I don't know, this is one level curve, right? F equals 1, F equals 2, F equals 3. This is the potential function, right? Now, in theory, I could draw in my vector field, right? I could draw in all of the vectors for my gradient. So here's my gradient, right? Now let's imagine that I wanted to take an integral of my gradient from here up to here, right? So I'm going to be like, oh, what's the integral of my vector field f dot dr over this path? Well, I hope it's kind of clear, right? I don't know why that says 33. Should just say 3. I hope it's clear that over this path, right? What am I doing? Well, if I'm taking the integral of this, what this tells me is that I don't actually need to consider the vector field. I know that it's a gradient, so all I need to do is use little f, use the scalar potential. Which tells me that, well, I ended up on the 3 line and I started at the 1 line. So the value of this integral is going to be 2, and it's going to be 2 no matter, as long as I start on this 1 line and I go to this 3 line, it doesn't matter what path I choose. It doesn't matter at all what path I choose. A lot of these integrals, like our one from the warm-up, are what's called independent of path. So rather than having to calculate the whole line integral, what it turns out we can do is, if we have a conservative function, all we have to do is identify the potential function, little f, evaluate it at its endpoints, and subtract. We're basically just finding the antiderivative here, where the gradient, like kind of undoing the gradient, finding the potential function, is sort of like reversing our gradient. I know we've only got a couple minutes before I'm supposed to switch. So I just want to talk through this real quick. If you need to log off, again, this stream will be going live soon. All right, so let's try this. And I know this is a little weird. For calculating this line integral. So here's our vector field. It's xy squared I hat plus x squared yj hat. And what we're doing is we're moving from the point 3,6 to the point 2,2 along a particular curve. And the curve we're following is going to be this one. And I'll y equals x squared minus x from the point 3,6 to the point 2,2. And you might say to yourself, Mr. Bates, that seems a little bit backwards, and that's just fine. It's just fine for it to be backwards. So here is the curve that we are following. Here's the curve that we're following. So in general, I would actually have to do kind of a messy integral to solve this, right? I'd have to like, you know, figure out what r prime is and take the dot product and parameterize and everything. But if this is a conservative function, my life's a lot easier. Well, let's ask ourselves, is it a conservative function? Can we find a scalar function whose gradient is f? And it turns out we can. And if we propose the scalar function, little f, our potential function, as 1/2 x squared y squared, you'll notice if I take its x derivative, I get xy squared. If I take its y derivative, I get x squared y. So what this means is that instead of doing this whole integral, all I have to do is say, well, I want to end at 2, 2, and I want to start at 3, 6. Why did I write a 1/2 there? Good question. I was thinking too far ahead. Minus f of 3, 6. And that this is going to be equal to the line integral of the whole big vector function over that curve. Well, this is a lot easier. I just plug in some numbers, right? 1/2 2 squared times 2 squared minus 1/2 of 3 squared times 6 squared. And I can do that. That's 2 squared times 2 squared. And then I divide that by 2. It turns out to be like a pretty big number because 6 squared is you know, big. This turns out to be negative 154. But still, I get my number really easily. I get my number very, very fast and very, very easily using that. So the fundamental theorem of line integrals is great because all you have to do is evaluate the potential function at its endpoints. And this is what we call independence of path, or IOP. So in this case, this is your best buddy. This is something you really want to pay close attention to when your integrals are independent of path. So what this means is that an integral that's independent of path will have the same value no matter what path you take. So I would get a negative 154 no matter what path I take, as long as I have the same start point and end point. No matter what path I take, as long as my start point and end point are the same, I get the same number, I get the same value. These are what are called independent of path. That the integral of a conservative field depends only on where you start and on where you end. And this property is called independence of path. The very first way we have for deciding that things are independent of path is that we say that line integrals of conservative vector fields are independent of path. That, again, they only depend on where you start and where you end. There's other things, though, also that tell us that you're independent of path. One of them, for instance, is let's say f is independent, the integral is independent of path. What's the value of the line integral around a closed curve? Well, what if I start and end at the same point, right? What if I start and end at the same point? In that case, my line integral of big F dot dr is just going to be equal to, well, if it's really independent of path, then it's going to be equal to the value of the potential function at point B. That's where I end, minus where I start, and I should get nothing. So if I have a line integral that's independent of path, it will be 0 for a closed curve, for a closed path. So if I basically walk around in a circle, I end up right back where I started. The work done by a conservative force field as it moves around a closed path is 0. So, yeah. So we've got a couple different things, and we'll actually add more to this list. But it turns out that if our functions are independent of path, if our integrals are independent of path, that's the same as saying f is conservative, which is also the same as saying that its line integral is equal to 0 for every closed curve C. And turns out there's more. What's up? That's fine. So just to finish up, there's one more criteria we could use. So far, we've been trying to just come on. It's fine. Just come on in. So far, we've been kind of hacking it by trying to guess what our potential function is. We can actually demonstrate one way that something is conservative by, instead of trying to go up, going down. So what happens if we take some partial derivatives like this? The x derivative of q and the y derivative of p. Well, it turns out that, we're supposed to have some, if this thing is in fact conservative, right? If our vector function is in fact equal to the gradient of some scalar function, then p should be, the x derivative of that scalar function. Q should be the y derivative of that scalar function. So if we take the y derivative of p, it should be like taking, fxy. And if we take the x derivative of q, it should be like taking fyx. But remember, by Clairaut's theorem, in general, those are equal. So one way to test if a vector function is conservative is if py is equal to qx. So if we kind of look at, from the warm up, x squared I minus yj, we had, well, in this case, p is equal to x squared, and q is equal to negative y. So what is px, or py? Well, py is 0. Qx also turns out to be 0, and that works out. If we have, what was it? Xy squared I hat plus x squared y j hat. If I take the y derivative of this part, I get 2xy. If I take the x derivative of this part, I also get 2xy. So this is a quick way to check if something's conservative. You get to take the cross derivatives, right? The y derivative of the I hat part and the x derivative of the j hat part, and you get your thing. Now, this does have a little caveat to it. This is only really true if your region has no holes in it. It turns out that we will see some examples where py equals qx, but it's not independent of path. And those are always fun, and it turns out that that's because there's a hole in your region, and we'll talk about what that means. But that's kind of the short version of all these things. So I got to kind of wrap this stream up and get ready for physics. So I'm going to go pull down the stream for a second, get everything set up for physics. I'll be back up in a couple of minutes. I'm sure that there's millions of questions. Please check out my MCPS. Send me messages on Remind. Send me emails. I'll put up a link for 16.1, and we will get there. All right. See you in a bit.